First, thank you for the Lattice team for this opportunity to represent the Caliptra community, to present what Caliptra is and the challenges that we are facing, and especially the security team for insisting that I should be here. So before I proceed, I really want to thank for the privilege to be here in behalf of AMD, Google, and NVIDIA. There are some really great partners and colleagues and technologists that are working on this behind the scenes. I just happen to be a voice of them. Before I proceed further, let's just talk about what a root of trust is. Maybe some of you are familiar with it, some of you are not. Like when I think about it, the way I think about it is in a physical sense, what a driver's license or a password is. If you think about your driver's license, that provides an identity that is unique to you. Its measurement essentially means that your address that says, hey, I live at this particular place and the driver's license carries this. Life cycle is an expiration that exists on your driver's license. And the ownership is the signature that you sign on the driver's license to say that belongs to you. And the attestation is when you go to a bar, when somebody runs that through the database, they would know that, hey, you can be here and you're 21 years and older. I'm sure we're all 21 years and older. But nevertheless, when somebody asks for my license to see if I'm of the right age, I like it. Anyways, so from a Caliptra point of view, essentially Caliptra provides these specific capabilities from a root of trust angle. And in order to do that, it's not just a specification, it is implementation of the specification in a consistent and a transparent manner, which I will talk more about it. Moving on, so the most common question that everybody asks is, hey, every SoC carries a security controller. Why do you need to do something unique or something different, right? The way to think about it is, if you think from a server ecosystem point of view, if you think about a blade, a server blade, we may have as many as 40 different components on it: SSDs, AI accelerators, FPGAs, CPUs, SSDs, BMCs, whatnot, right? So what has been happening is each of them carry a different set of solution, which essentially means that there is a fragmentation. And given our view, as a server view, we observed some deficiencies, not intentionally, but because of the understanding of the specification and what has been provided. So that's essentially when the partners have come together and they decided that we need to help the server ecosystem as a starting point to make sure that we have a consistent solution. So as a part of it, Caliptra, which translates in Spanish to a root tip, is an open source silicon root of trust that has been devised. And the two primary things that we want to achieve as a part of it is consistency and transparency, which I'll talk about it in more detail now. From a consistency point of view, think of it from a customer experience. What I mean by customer experience is, like let's say I have a server, and the server could be used by customer A versus a customer B. Each of them have a different set of requirements. You don't build these blades depending upon each customer, which means it cannot be managed, which essentially brings out to saying, hey, how do we ensure that even the most security-sensitive customer to a customer that trusts Microsoft that it would do the right thing, or Google that they would do the right thing, how do you ensure that you essentially have the same experience for them, right? That's where, from a consistency point of view, you want to have a homogeneity in terms of how the solution would look like, right? The second part of it is, as we go towards confidential compute, each of the tenants, as in the folks that use the VMs, they do expect to see what the device measurements look like, how the attestation reports look like, and all that story ties back to many things, but it fundamentally ties down to how the root of trust would look like. for anybody that has done security, taking an example of TLS and SPDM, one of the things that you might have observed is if when silicon hardwares and firmwares do this, which are custom, you would always interpret that specification in different ways, and you implement the same thing with the right intentions, but the output of what it provides is unique and different, right? What does it mean? Like from a customer point of view, whoever is doing a confidential VM, when they write their verifier to see, hey, what does this report mean? What does this report say? They would have to write a different verifier or an attestation verifier for each of the device measurements that they would see, right? In other words, the customer experience from that small example is not the most pleasant thing. The other thing that is important, which I would talk about, is functional consistency across operational flows, right? Like if you think about, I have an SSD in a fleet, when should that SSD be decommissioned? When it is being decommissioned, what should we do, right? What I mean by that, ultimately, at the end of the day, everybody is after the data. The data would be either LLM learned data that is very precious in nature. It could be our social security number that is sitting as a data. Everybody is after data, and the primary goal for all of us is to ensure that data is protected while processing, in transit on the network, or it is sitting steady state in an SSD, which essentially means that you want to have a consistency how these devices get decommissioned, how they are operational, how they would be debugged within the fleet to make sure that we have essentially the same set of operational procedures in order to do that. Moving forward, let's talk about transparency. While talking about transparency, I want to quote, I'm going to kill this French pronunciation, but I'll try my best. His name is Augustin Krichkovs. He wrote in his book called, it's a La Cryptographie Melteria, or Melterer, right? I got my French pronunciation wrong, but his key message is secret keys, not secret algorithms. That's essentially what the underlying story that we want to take away as a security community is to ensure that when we are building something, we are trying to build a lock. Lock specification can be consistent, it can be constructed, but the keys that we use in order to unlock a room is essentially the most secure thing of this story, right? And this is where transparency is important for software developers. You've been used to having crypto libraries available online, and you reuse, and there is no security in it. Anybody can see it, anybody can audit it, anybody can try to find a hole in it. The goodness essentially is achieved the underlying users, which is you and me, to make sure that our data is secure. And that's the same thing that we want to achieve as a part of providing this hardware root of trust, an open entity, to make sure that the algorithms, how our keys are protected, how the algorithm is done, how it has to be implemented as an open root of trust solution. Now, I would also want to say that for folks that are familiar with it, with Caliptra, are there additional improvements that needs to be done, like how Lattice has been talking about lower power, right? Absolutely, yes, right? But the goal, everything is a step function. You essentially try to make sure that the industry understands your solution, they're comfortable with the solution, because unlike, no offense to software, but unlike software, from a hardware point of view, you make a mistake, it's there for 4 years. It's uncorrectable. So we want to make sure that the first function of Caliptra is a function that is secure in nature, is simple in nature, that it can be absorbed and integrated and be present in the server ecosystem in 80 to 90%, if not 100% devices, and then essentially do the due diligence of whatever needs to be done to make sure that it goes into a low power applications also. Anyways, I think going back to the transparency thing, the way to think about it as transparency builds trust. If everybody knows what is going in, what is coming out, you would know that it's a right, essentially the chips carry the right security solution. And again, to go back and say, it's not that people that have been working on the security and doing the security solution for any of the SOCs, they have been doing incorrectly. It's not the message, right? The message is, as a security community, we want to make sure that solution is transparent and consistent in nature, and we build our innovation on top of these basic functions while keeping the underlying chip secure in nature. Moving forward, quantum threat. Let's see. Let's make sure that everything comes in. From a quantum threat point of view, right? Today, the RSA and ECC algorithms, which are considered as classical algorithms, in a classical computer context, that math is completely undefeated. Like, you can't mess with it, you can't do anything with it. But when you come to a quantum computer, which is always under debate with respect to when it happens, which we can talk about further, a 20 million qubit quantum computer can potentially defeat RSA-2K within 8 hours, right? There's been good amount of research done on that, and from a numbers point of view, people agree. Now, what does it mean? What it means is any algorithm that we have, or any technology that we have with respect to quantum that uses pre-quantum algorithms like ECC and RSA, be it confidential compute, TPMs that are used, root of trust that used anywhere, key exchange protocols like TLS that is used for our HTTPS connections, right? Our SSH, secure boot, everything is fundamentally broken, right? There is nothing that exists in the current chips or ecosystem that will protect against post-quantum. Now, this is the fundamental question people ask. What is the state of quantum today, right? There have been articles that get fed through, like, if you take your phone and keep saying quantum, quantum, it will feed you a bunch of articles, right? With all the clever AI generation that happens these days. But you would see that right now, wherever the frontier machines are, around 1K is what they say. And these are published information, right? What is not published is state actor information where the work is done in private and where they essentially are at right now. But what we have observed is year over year, it's about 2 to 3x. Just like the transistor technologies, when it started, it was very slow. And once it started picking up, once there is a market demand of having such a compute, it essentially sped up quite a bit, which we all know. And from the quantum point of view, yes, right now it's not a threat with the known public information, but that does not preclude us to sort of see where the history was and assume that the history would repeat. And there is information, or there may be information that we all don't know about, and where the quantum work is being done in order for a better compute power to happen. Continuing. So what is the problem today, right? The problem today essentially is, the way to think about it is harvest now, decrypt later. If you think about key exchange protocol, even though AES itself is non-compromisable from an attacker point of view, the underlying protocol that is used to do a key exchange and establish that key is still a classical key, that classical algorithm. So when you use a classical algorithm to do Diffie-Hellman and establish the key, that particular key itself can still be compromised when the post-quantum comes into play. So what do folks do right now? They just sit there and listen. All you need is large amount of storage. You are looking at a network. You're taking the content, and you're stashing it elsewhere, right? You don't have to do anything else, right? And when the quantum computing is available, the goal is to essentially go back. Now you can find the key, and you can decrypt the content and see what the content is. And that's essentially what the harvest now and decrypt later strategy or the cyber threat is that we need to protect against, right? And this is where, and there has been a lot of public information that Apple, Google, and Microsoft have published on this, and some of the articles are right there for us to go look at it for ourselves. Going forward from a quantum resilient cryptography. So from a post-quantum point of view, there are two things. post-quantum readiness, post-quantum resilience. Post-quantum readiness is where you use like LMSS or XMSS algorithm to do a firmware signing, and post-quantum resilient is where you want to have true post-quantum algorithms like a dilithium or a Kyber or NIST-approved algorithms to ensure that we are truly doing the post-quantum computing or post-quantum crypto to protect against post-quantum computing. So there's been a lot of research around this, and NIST has finally initiated its research around 2016. And earlier this year, 2024, in August is when they finalized which algorithms they're going to be supported and which algorithms they expect the quantum resilience to be. Now, before I proceed further, there is always this transitional time where everybody is afraid of the math to see who can and cannot crack it. And there is always a hybrid time where you want to do both classical and post-quantum to be present. And all the standards that are being defined as a part of this is essentially figuring out how do you do hybrid or composite signatures, how should the certificates be, like twice the amount of work for the customers to do both, trying to figure out this is the classical one, this is the post-quantum one, how should the composite signature would look like, and all these standards that are being played. Right now they are under works to make sure that you essentially have a hybrid transitional time so that if the post-quantum algorithm gets cracked, you have a classical that you can still fall back on. And there are multiple options of post-quantum that are happening. So it doesn't mean that you do one algorithm of post-quantum, you're nice and safe. You still need to keep yourself on top of the curve to make sure that you have other algorithms included. So this is the Department of Defense NSA timeline that, from a US government point of view, that if we have to have products that meets the requirements that we need to adhere to, right? They have put it out there saying that from a software and a firmware signing point of view, they want that to begin immediately by 2025. And there are quite a few chips out there that support XMSS and LMSS for firmware signing. This should not be a news. If it's a news, we are in a worrisome state right now. And their statement is, while you can have classical and XMSS at the temporary time, by 2030, they wanted everything to be post-quantum ready. From an equipment point of view, they say by 2026 is when they prefer some of this readiness to be there, and by 2030, they want to get to post-quantum ready phase. From an operating system point of view, they have published the timelines, but the most critical thing that for us to notice that I should have put it in red is they recently published that by 2035, they want to can the classical algorithms, which means from a silicon point of view, we should at least have these by 2030 so that at least by 2030, if not early, so that we have enough learning from silicon point of view, from our customers' point of view, from standards point of view, to make sure that we have a couple of revisions in. I'm going to switch topic and say I spoke about all this stuff. What is it that Caliptra is doing as a part of it? With respect to Caliptra, in 2.x generation, we are implementing a subsystem that essentially resolves and provides multiple of these capabilities. The first thing is we essentially put out an open source module called Adams Bridge that supports post-quantum cryptography. We essentially have dilithium. You should be able to see it in the public right now. It's at 0.8, 1.0 should be pretty soon, followed by Kyber algorithm on the same thing. And it is essentially providing for free on Apache license to the community because, going back to what I said, secret keys, not secret algorithms, to the ecosystem. Now, obviously, somebody may take that particular one, have a low power or have a high power. They can always modulate it, but essentially, we are providing an open source one out there for folks to use it for the root of trust, accelerator, whatever they want. From a post-quantum capable root of trust solution point of view, we are integrating that into the Caliptra 2.x subsystem to make sure that we provide a post-quantum resilient solution to the ecosystem. We also implement OCP, owner authorization and ownership transfer, which is like, in other words, having a dual signing to make sure that a manufacturer is signing the firmware, on top of it a tenant or an owner of the device is also signing the firmware, and provide the owner device transfership to make sure that if manufacturer has a device, the device being transferred to somebody else. Like, think of it as I went and bought a device from Costco, and once I get it, I don't want that specific device manufacturer to control it, right? You want to have a ownership of the device, right? So essentially making sure that capability exists. We also integrated the Fuse controller and the lifecycle management. To go back, decommissioning servers is extremely important. It's a critical step. What happens to the device at the end of life is extremely significant to all of us in this room. From a OCP streaming boot point of view, that's essentially a new technology that OCP has come out with to ensure that the firmware is not necessarily sitting in the flash, but the latest and greatest firmware can be supplied to all the servers and the devices that are in there to make sure it's always security compliant. We also provide OCP lock support, which is a new technology from an SSD point of view, how the data should be encrypted, what keys should be used, and how those keys can never be compromised. And as I always said, data is what everyone is after. Where does Lattice play in this entire story? As you all know, and you've been using, and everybody has been speaking, they are sprinkled everywhere. People use it for as basic as controlling the reset and boot of each of these signals, of each of the SoCs. You use them for managing the vias to increase or decrease, manage fan power. If you're using it as a BMC, you have it as a platform root of trust. So as an FPGA and CPLD, as Lattice, these devices are used in many places, and most places is actually functional critical, right? If a particular CPLD or FPGA is compromised and somebody goes and switches off, if I may use the term, if it's not too early, CrowdStriked, right? Everything is gone, right? No offense meant, but anyways, so this is the reason why we want to make sure that some of the fundamental capabilities, like a streaming boot, a strong PQC capable ROT, and other things are part of the CPLDs and FPGAs, so that whoever is consuming them, using them, can use them with a lot more mental peace of mind. And first of all, and as a part of it, I want to thank Lattice for the steady partnership that you guys provide to us, and listening to us and taking feedback from us as a OCP community. And I'm looking forward to work with you as a part of Caliptra and go from there to see what we can do for you. Thank you, guys.